Hi there, welcome back. This is the second in the series of restoration of this Philips BX626Z, which I opened and had a first look at in the first video. And before I go any further, I just want to correct a few errors which I picked up when I looked at this further. If you recall, I said there were 6 bands, and I thought one of these selections here would be the gramophone. As it happens, it's not. This thing has got 1 medium wave band and 5 shortwave bands, which I could very easily have discovered if I'd looked at the service manual first. The wave ranges: medium wave, shortwave 3, and then there's 1, 2, 3, 4 shortwave 2s they call it. This is the frequency ranges in meters and in megahertz. So this thing goes from 517 kilohertz. First band goes to 1.6 megahertz. Then you've got there's a slight overlap there to 5 megahertz, 5 to 9.3. Another slight overlap, 9.1 to 13, 11.6 to 17, 17 to 27. So we've got a continuous tuning from 517 kilohertz all the way to 27.3 megahertz. So this thing is quite feature-rich. Now, what does that do to the option of the phono? Well, that too would have been obvious if I'd read the controls properly. Knob 1, volume and main switch. And that is actually the first mistake. I thought the knob itself was not a switch. I thought that was just a volume control, but there's a main switch on there. And then the lever below, which I thought was the power on, is the selector between radio function and the pickup. So that is the first error that I made. Tone controls, we got that right. Fine tuning, we got that right. Wave band switch, wave range switch, we got that right. And the main tuning, that's fine as well. The other error is that I thought that CAN was some kind of voltage inverter to step up the voltage from 6-volt battery power to the mains. Well, it isn't. It's actually an output transformer. And that's obvious because this thing has an output transformer like just about every radio we've worked on. And I didn't see the output transformer on the underside. Just overlooked that sort of thing. So that is the output transformer, and that is obvious because this schematic here shows the coils inside the output transformer. And if we look at the actual layout, we see that exact CAN here with exactly those coils. And this is further confirmed because when I followed the signal, when I put in a signal to do the testing of the output transformer, this is where it came to. So that's an output transformer. So far I've seen nothing to step up the voltage. And quite honestly, I haven't really looked because the first test I did was to check that the power transformer was working, using the method that I've described in one of the building block videos I've done, and I'll link to that just above. You can look at that in detail. The trick is to test the mains transformer, the power transformer, and the output transformer under safe conditions before you even power this up. So that proved to work. So the power transformer is fine, and so is the output transformer, which is that CAN over there. And I've never seen one of these in this format inside one of these radios, so that's quite an innovation. Which leaves us with the question of 6 volts powering a mains level voltage radio. But we'll come to that later, I think, when I start looking at the details. The first thing I want to do is to make sure that we've got a workable radio here, and I'm always anxious to get the first power up done. So far we have the power transformer tested and the output transformer tested. Again, the way I do that is in the building blocks. That's linked to above now. And so we know that two of the main components are fine on this radio, which means we've got to go. So now I've gone one step further, and I actually connected the mains to this without the rectifier tube. And I found that I had mains voltage arriving at the two anodes of the rectifier tube, and I had heater voltage. So I know the transformer is working, the switching is working, so far so good. Now when I say the switching is working, the power switch here is on. That's the bottom one, this is the top one, so that is on. Volume higher up means the switch is on. And the switch at the back here, there's that switch that was at the back that selects between battery power and mains power or off. That is obviously on mains power, and we're getting voltage arriving at the anodes of this tube. So what I need to do now, and we're going to do this together, is I'm going to power this radio up without the valves. I'll make one exception. I'm actually leaving the magic eye in here. No big deal. We leave one tube in so it draws a little bit of current, and it also draws a little bit of high voltage, B+, and also draws a little bit of heater current. Nothing else should be drawing current except for losses, and I'm sure there's lots of them with all the leaky capacitors we've got on here. But so we shouldn't have much current after the initial power up when it charges the capacitor, which is that guy over there. We've got two sections, each of them are 50 microfarads, according to the schematic and according to the labeling on the capacitor itself, and we'll see what happens. We'll follow the power up. There are no tubes connected other than, as I said, the magic eye, because then I want to check to see what voltages I'm getting on here. Make sure that the B+ is there. So let's get ready for that. Now you might have seen this before. This is my dim bulb tester or lamp limiter, and it's also got an isolation transformer in. We don't really need one for this particular radio because it does have a transformer. It's not a hot chassis set. But what I do here is I power this in here. That's connected to the power cord of the radio. And what this does is I can put in 40 watts, 60 watts, 40 watts, 60 watts, or any combination of those. Activate that to limit the current into the set. I've got the switch on limit. It's off at the moment. I can activate 1, 2, 3, or 4 bulbs at the moment. I'm going to activate just the first one. And what should happen is the inrush current to charge the capacitors should light that up. It may even not light it up if it's very low current, but sometimes, usually it lights it up. It then goes dim, and then usually what happens if there's tubes in there, it starts glowing again as the current draw increases. In this case, we don't really have tubes except for the magic eye, so I don't expect to see that phenomenon here. But I'm putting on the maximum limit, which is one lamp in there, the smallest wattage lamp. This is the maximum current limit possible. It's on limit. We'll read the voltage going to the radio there and the current being drawn when I flick this on. Now, this thing I built, and I logged the build of this in 2 previous videos. I'll link that on the top as well if you're interested. So let's go. See what happens. If there's a short, this thing will light up very brightly and I can immediately switch that off. Let's see. Oh, of course, I've got everything limited, so let me activate the first one. Okay, what do we have? We had such little current. Either it's not getting anything. It is, actually. I should have 230 something volts here, the mains. The set is seeing 222 volts, and it's drawing 70 milliamps. Now, this 70 milliamps is probably losses. The magic eye is actually glowing green a little bit, but there's some current going to the magic eye, and there's some heater current going to magic eye as well. The rectifier tube's drawing heater current as well. So we should have B+. There is some limit because this lamp which is on here is limiting that from 235 or so to 223. If I activate the second one, so I'm putting 100 watts in series, look what happens to that voltage. It limits less, and it's now at 228. But let me leave it at maximum limit, and we'll see what voltages we've got here. So what happens here is the AC output from the transformer is actually the blue and the red wire, goes to the anodes of the rectifier tube. The heater voltage for the rectifier tube is this set of yellow wires, and the actual DC rectified voltage is taken from one of those heater wires. So there's actually a connection not up there but right at the transformer. Now this, of course, because the transformer is then referenced to ground, this is reference to ground. So I've got the voltmeter connected to ground over here, and I'm going to test right there, see what we get. DC voltage 343 volts. So we've got B+. It's pretty high. Well, yeah, it's pretty high because there's no current being drawn. This thing should be about 260 when it's fully operational. The B+, this is the first B+, because it then goes through another resistor and the second capacitor. So 343 volts. Let's see what AC component we've got on here. Should have a few volts. Whoa. Whoa, we should have a few volts, but not that much. Well, this tells me something. This tells me that the filter capacitor is not particularly healthy. We should not be getting that much AC ripple on our output here. Because what happens is the rectifier tube rectifies, sends the B+ to the first filter cap, and then the first filter cap filters that out, and we should be getting, well, a couple of volts. So it looks like the filter capacitor is not doing its job, which isn't surprising. This thing is 60 something years old. I could try something. Let me try something. Right, we're going to try something. Now this is where those warnings come in. Do not try this at home. There are dangerous voltages here. You can kill yourself, you can fry yourself, you can make your wife a widow. All those warnings are very, very important. I know I make light of them, but after the few shocks that I've got, I tell you, it's not fun. So be very careful. There's high voltage in quite a few places right now. What I've done is this. I have, actually there isn't right now because I switched off the set, but there will be when I switch it on. I have got a 47 microfarad capacitor here, just out of the junk box, and it's working, I know that. I've connected it between ground with this black crocodile clip, and the positive is connected to that output there, which is where the first filter cap goes, okay? And so I'm going to, just to be safe, I'm going to connect this, the multimeter, to there. I'll do it at the capacitor because I've got more space. So what we're going to do now is switch it on, and we'll measure the same voltages. First the DC voltage, and then here goes. There we go, it's going up. And it's actually, I believe it's a bit higher actually, which makes sense because that this is RMS, it's a true RMS voltmeter, so it's actually gone up. Now let me put it on AC. Bam, 0.4 volts AC. So what have we done here? We've done something we shouldn't do. We've put a good capacitor in parallel with a bad capacitor. That the actual C1, the first capacitor, the first filter cap on that can is messed up. I've replaced it really with this one while leaving the other one in parallel, which is fine for testing, but you shouldn't run this for long. And what it's done, it's now started doing the job that that capacitor should be doing, and it's actually filtering the ripple. So we've got a minute ripple voltage over there. That will go higher when this thing starts drawing current, but that is more like it. That's definitely more like it. So okay, first problem to solve, we need to replace the filter can. And I am not sure if I'm going to restuff it or replace the or connect the capacitors elsewhere on the underside. I'm certainly leaving the can in place. I don't want that to detract, or its absence to detract from the original look of this thing. But I'll go on the underside and see if it's easy enough to fit two capacitors. I'll do both, obviously. 47 microfarads at 450 volts or so, and put them in where the original filter cans are. So we can sort this one step at a time. Just to confirm that that is indeed AC ripple, there's an easy way of doing it now. We've done some of the safety checks. So what we can do is just put in the power tube, just the power tube, and I'm going to do that. So just the power tube, there's no preamp, none of the other tubes are in place. I've also got the speaker wires connected to this clip-on connector, to which I'll connect just a speaker, and we're going to see or hear if we hear ripple, if we hear the hum. Now, what should we hear when we switch this on? This is not audio, it's not the AF you're listening to. This is simply the hum that goes from the B plus to the power transformer, or rather to the output transformer, and then through the power tube. So we should hear quite a bit of noise, and it's not dependent on the volume control. So let's see what happens. I'm going to switch it on again with one lamp only. And we've got a bit more current. No, we don't actually. We still don't have much current because let's see, I don't know if that tube is working. We'll know soon enough. Yep, the current's gone up, the voltage has come down. That's glowing very dimly. So our power tube is actually passing current. Let's see what happens to... Is there any noise? No, there isn't. Oh, of course there isn't. There isn't any noise because I still have that capacitor connected in there. What happens if I remove that capacitor? So we're left with just the original capacitor, and what I'm going to do is I'm going to remove it from the negative end. See what happens. There we go. That is 60 hertz. Well, actually it's 120 hertz hum. Put that cap back and it's gone. Brilliant. Brilliant. Okay. First problem we know how to solve. We'll just replace the capacitors, the two filter caps. So I'll get on with that. Okay, so I've swapped out those, or rather I've inserted two new capacitors. They are 47 microfarads and high voltage as well, obviously. And I've put them on top of where the filter can was. So it's in the same location approximately, and wired the appropriate wires to each one. The grounds are tied together and they are securely soldered to that piece of the chassis over there. So this is exactly the same thing as what those two caps in the filter can are doing. They are basically hardwired or screwed on to the chassis at that point approximately, so this should be exactly the same, except it should work. What I've done now is I've just connected the multimeter to the first point, the first capacitor over there. That's the B++, the highest voltage, and we're going to switch it on and see what happens. I've got the speaker connected just so that we can hear if there's any hum. Let's go now. Should start dropping because the power tube is drawing current. We're at 150 volts. It's drawing about 100 milliamps. And we have no hum at all. So that's the first problem solved. Looks like that was a success, and I think we're ready to look a bit further, look for B pluses everywhere. But before I do that, because I then want to do the first power up, but before I do that, I'm going to replace two capacitors right away. Let me show you. There are actually two capacitors here that I'm going to swap out because it'll avoid any major damage if they're leaking really badly. Now, if we look at the schematic, this is the whole schematic and this is the output transformer over here. And if we go in, we see the following. We have the output transformer here being fed by the power tube, the anode of the power tube. There's B plus coming in, or B plus plus as they call it. This is the highest voltage coming from that first cap. That comes through the output transformer, and it feeds the anode, and that's where the signal is generated, the output signal. The input to that power tube is through the grid, which is through this resistor R22, and it's basically a voltage divider here. The R21 goes to ground, and it comes from this capacitor here, C55. Now that guy I want to change, because if this thing is leaking, then what it's doing is bringing, here's my B plus, it's going to be bringing high voltage through that capacitor to the grid of that tube. Now the grid of that tube has got to be negative in relation to its cathode, and if this thing starts leaking, that'll go up and it'll basically open the tube up completely, like opening a tap, and the current flow through here would be dramatically high. Now I don't think it's happening because we've had this tube in already, and that B plus was still connected, although this tube was not there. So, but still, I'm going to change that one. And the other one, which could have a similar effect, is the cap feeding this guy, because this is the preamp, and it acts as a preamp to drive the power tube, and it is fed onto its grid from here, through capacitor C52. Although that's not necessary, that's low voltage, isn't it? Yeah, that's low voltage. Okay. The only one to be seriously worried about is this guy over here, and I'm going to swap that out before I put in any tubes, just to minimize any risk here. Just to show you very quickly, this is the schematic I have, and as you can see, the power supply here is pretty simple, very straightforward. It comes in, there's a switch, goes to the primary. There is no voltage selector here, which is what we have on this radio. There is no battery option, no switching, nothing like that. So obviously this is a slightly different schematic. Then we have the secondaries. We've got a dual secondary. The center tap goes to ground, and the two go to the anodes of the rectifier tube, which we know is working because it's producing B plus. The heater for the rectifier tube is this S3. That's usually about 5 volts, and the one point of that is really the B plus. This is the cathode, directly heated cathode. So our B plus comes out here. It emits a positive of C1, which is one section of that filter can, which we've replaced. It produces B plus plus, goes through a resistor to the second section of the filter can, which we've replaced as well. That is B plus. And then we also have the L2, this is S4 rather, this is the other secondary, low voltage secondary, which is heater voltage of 6.3 volts, and it also goes to the dial lamps. And that is referenced to ground, as you can see. This dotted line around here shows a ground point. So basically that's a very, very simple power supply, nothing like what we have here. Then of course we have that B++ coming in here, feeding the primary of the output transformer, which in turn then feeds the anode of the output tube. And the B+ is the second level of of high voltage, which is slightly more filtered and slightly reduced, and that comes in there to feed the anode of that tube. It also goes to quite a few other places. Here's another one. It goes into that IF transformer through that coil, and it feeds the anode of that tube. Quite a few places it'll go to. If you follow it, you'll see that there it is again. It feeds that magic eye, that's B+. So B++ is only really going to one place, and that is the it's only really going to the output transformer. Here's another B+ that comes through there and feeds the anode of that triode in that dual function tube. And I'm sure there's another one here. Here we go. There's another B+ through that resistor, through that coil, which is probably just a choke, and it goes to the anode of that tube. So yeah, okay, just a brief overview. And if we look at this, what we really have, this thing has got a lot of coils and trimmer coils and trimmer caps. But basically what we have here is the RF front end. The antenna comes in here with an earth connection. The RF front end is tuned, is selected. You select the tuning approximately for the band you're going to use. So this switch, this is one of the wafers in the multi-wafer switch we have there. That'll select or already pre-tune the front end for the band you're going to listen to. Then that goes through this RF amplifier. And this RF amplifier does two things. One is it amplifies that signal. So we should actually have quite a strong reception on this radio. Secondly, it acts as an oscillator. And am I correct? I think I am. Yeah, there's the one section of the tuning condenser. So together with these coils in parallel or in series, I'm not sure how that works, you tune the front end, and then with the second section of the condenser, which is this one here, you tune the oscillator. So the oscillator is going to be tuned slightly higher than that one by actually higher by exactly the IF frequency, which I believe is 452 kilohertz on this one. What happens then is the signal comes through here, gets amplified again, and it goes through. You see, I'm actually not sure what this section is. This is almost part of the oscillator as well, is it? Not quite sure. Anyway, once that signal, the IF signal, comes through modulated, it goes through this IF transformer, you tune that, it gets amplified by this guy here as well. It goes through the second IF transformer, and it then comes out and it finds its way to these two detector diodes on this tube. This tube has got two functions. One is a dual diode, which acts as detectors for the AM and produces audio, and the other one is actually as an AF amplifier, preamplifier. So that then all finds its way to here, which is the volume control. Signal comes out of the volume control. There's a few tone tapering circuits, the bass switch, for example. Those are all tone shaping. And that then signal comes through capacitor C52 and finds its way to the grid of this tube, which is the preamplifier. The other tone shaping that happens is on here, on the volume pot. There's a tap at one point with a resistor capacitor in series. What this does, it's perceptual loudness, really. They call it, they've got some funny name for it. But what happens is it reduces the treble at low volumes. So if your pot is tuned down here, some of the treble, some of the high notes coming through here get bled through to this point. So you lose them, which means your sound becomes more bassy and more mellow at low volumes. So that's sort of like it's almost like a loudness switch that you used to have. There's another control, which is this guy over here, which I believe this is the treble control. The bass is just a switch, but the treble actually rotates. And what it's doing is it's actually working on a feedback circuit from the output, and it feeds back through to here to either amplify or cut out some of the high frequencies. So you either have more mellow sound, so less high end, or you have the higher quality with all your high end when the feedback effect is minimal. So this circuit is a little bit more difficult for me to read than some of the German sets I've done. Not impossible. You can go through all the coils and check that that there's continuity. But what I want to do with this radio is as follows. I'm not going to do my usual stint. I'm actually going to check for safety, which I'm doing, and I'm going to continue doing that by checking for the B pluses at the various points. When I'm satisfied I have the B pluses arriving at the respective tubes, and I know that none of the tubes are actually shorted, and I know that safety cap has been, or that cap has been replaced, I'm actually going to power it up. And I'll tell you why. This has quite a few bands, but ultimately what it's trying to do is it's trying to create a difference between your tune frequency and your input frequency of 452 kilocycles modulated. So you're really aiming for one IF frequency. It's not like an FM where you got two. Usually got 460 or 455 or whatever for the AM bands, and then you've got 10.7 megahertz for the FM. This is simply AM. So you are looking for 452 kilohertz going through these modulated. Now, where they came from depends on the front end. Whether they came from the medium wave band or they came from one of the shortwave bands doesn't make any difference. So if we test this and it works, then why the hell should we go through all these coils, right? If it doesn't work, then we have to go through all these coils. And this service manual is very friendly. It actually gives us these drawings here. So when you've selected a particular band with the wafer switches and you remove everything that's superfluous from the schematic, this is what you have for that band, the 17.6 to 27.3. So you can actually trace the signal just through those components that you see here. Same applies for that band, and so forth, till you get to, for example, this one is for the medium wave. So depending on what we find works and what we find does not work, we can actually do the signal tracing on here, which makes it quite convenient, because that schematic part with all the switching in place and all the extra components that are switched out makes it quite difficult for you to follow the signal. So that's the idea. Basically take a bit of a shortcut. Obviously, if there are any fixed capacitors here, the ones that need to be swapped, they will be swapped out anyway. Any resistors that are visible will be checked just to make sure they're within tolerance. But I'm not going to go through with all the painting that I usually do with the other restorations, because this is actually a lot simpler to work on. It seems more complicated, but it actually is a lot simpler. One common source of problems with these sets is the wafers on these switches. These are all rotated at the same time, but there are a lot of wafers, a lot of contacts, a lot of oxidation goes on. So these things have to be very, very well cleaned. Sometimes just a little bit of tarnish can take the function away. So you've got to clean that pretty well. But it's actually a lot simpler and quicker than what I'm used to. So that's the plan. And I better get on with it.